Okay, we are recording. So as I was telling you, today we are going to see what is an IP address, and we are going to talk about IP addresses. And then make some exercise on IP addresses. Okay, so what is an IP address? An IP address is an integer of 32 bits. So here we can see an IP address. Since 32 bits is very long and a series of 0 and 1 is very confusing, we will break the IP address in 4 parts. The first byte that will have 8 bits, the second byte, the third byte, and the fourth byte. So each part will be a byte, and we will separate the byte with a dot. So this is an internet network. Here we have a router. This is a router. This is a switch. This is a switch. This is a PC. It's a terminal device for the network. So the PC need an IP address. So as you can see here, PC1 have an IP address. It's an integer of 32 bits. Here we have another PC, PC2. It have an IP address. Now the router on each interface need an IP address. So on this interface, which is, let me see if I can turn off just the one that is in front. Otherwise, people sleep. I don't like that. I don't think it's convenient like that. I think it's better like that. Can you come in front if you have any problem to see from back? Just come in front.
I'll be fine. I'll just split it.
The problem that if I put the light off, you start sleeping. I know that. So I think it's better with the light. I wish we have the possibility to just put the light off in the front, but we don't have this possibility, unfortunately, here. Okay? There they are. In the modules. Okay, so this is a router, and each interface of the router need an IP address. So for example, this interface is the gigabit Ethernet 0/0 interface, and it have an IP address. This interface is the gigabit 0/1 interface, and it have an IP address. We will see that this is a LAN, a local area network, as you can see here, LAN. This is another LAN, this is another local area network. Okay, and here we have a connection to the internet. Anytime we will represent the internet as a cloud, no? Where we have many devices, so we just hide the complexity of the internet in a cloud. So this notation for an IP address is called the dotted binary notation. Dotted because we separate each byte with a dot, and binary because we write each byte in binary. So since binary are very confusing for people, we have another notation which is called the dotted decimal notation. So this is exactly the same network that we saw in the previous slide, but this time, as you can see, PC1 have an IP address, and this IP address is not in the dotted binary notation, but is in the dotted decimal notation. So as you know, a byte will have a value between 0 and 255, no? So the first byte here, for example, is 192.168.10.10. Okay? For example, this router on this interface, the gigabit Ethernet 0/0, have an IP address, and this IP address is 192.168.10.1. Okay, so this is an IP address. It will be an integer of 32 bits. Sometime we will specify it in dotted binary notation, sometime in dotted decimal notation. So conversion, we saw some exercise last time, so you are familiar. For example, if I talk about 1234, you know that this 4 is associated with the 1, which means 10 to the power of 0. This 3 is associated to the 10, which is 10 to the power of 1. This 2 is associated to the hundreds, which is 10 square. And this one is associated to 10 cube, which to 1000, which is 10 to the 3, no? 10 cube. So you are already familiar with that. And as we work with base 2, we can work with base, as we work with base 10, we can work with base 2. So you need to know the power of 2. So for example, 2 to the power of 0 is 1. 2 to the power of 1 is 2. 4 is 2 square, 8, 16, 32, 64, 128, 256, 512, 1024, 2048, blah, 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 blah. Okay? We need to know them at least up to 2 to the power of 12. You should have that in your mind because we are going to use a lot of binary number in this course, no? So let's see. In the IP address previously, the first byte was 11000000, and this is the dotted, this is the binary notation. So as you know, this one is associated with 2 to the power of 7. And 2 to the power of 7 is 128. So which means that 128 is present in the sum that you must do. This one is associated to 2 to the power of 6, which is 64, which means that 64 is in the sum. This position is associated to 2 to the power of 5, which is 32. Since we have 0, 32 is not in the sum. 16 is not in the sum, 8 neither, 4 is not there, 2 is not there, 1 is not there. So when you have 11000000 is 128 plus 64. I will say 128 is there, 64 is there, and that's it. I will not say anything for the other one, no? So it's a way to convert rapidly from binary to decimal, no? So this is an IP address in dotted binary notation. For example, we have 11000000, so it's 128 plus 64, which is 192. Here we have a 1, so we have 128, we have a 0, we don't have 64. We have a 1, we have 32. So it's 128 plus 32. 128 plus 32 is what? 160, no? We don't have 16, but we have 8. So 160 plus 8 is 168. So this byte is 168. Here, 128 is not there, 64 is not there, 32 is not there, 16 is not there, 8 is there. 4 is not there, 2 is there, and 1 is there. So it's 8 plus 2 plus 1, which will be 11. So this byte is 11. On the last byte, 128 is not there, 64 is not there, 32 is not there, 16 is not there, 8 is there, and 2 is there. 8 plus 2 is 10, so this is 10, no? So the IP address is 192.168.11.10 in the dotted decimal notation, no? So this is just explain you what we already did, so I'm just going to skip it. So for example, here 11000000 will be 192. This 10101000, 128 is there, 32 is there, 8 is there, will be 168. This 00001010 is 10. Oh, the other IP address was 11 here, no? Yeah, it was 11. It's not the same IP address. Okay, this one is 10, and then this one is 11. Okay. So an IP address can be divided in two parts. The left part is called the network part, and the right part is called the host part. So for example, here we have an IP address 192.168.10.10. On the left part, we are going to split the IP address in two parts. The left part, which is this part, and the right part, which is this part. So this left part, we are going to call it the network portion. And this right part, we are going to call it the host portion. So all the devices that belong to the same network have the same network portion. The network portion is going to be common of all the devices that belong to the same network. But they will have a different host portion. So we can make the difference between one host and another host within the same network. No? So to know if a bit belongs to the network part or the host part, there is something that we call the net mask or the subnet mask. And the net mask will be a series of 1 followed by a series of 0. And when we have a 1 in the net mask, it will mean that the bit associated in the IP address will belong to the network part. So every time that I have a 1, the bit associated belongs to the network part. And every time that I have a 0 in the network mask, the bit associated in the IP address will belong to the host part. So the net mask is also an IP address. It's also a series of 32 bits. If I want to say that these 24 bits belong to the network part and this 8 bit belong to the host part, what should be the bits that I put in this part for the net mask? What value should I put? I should put 1, and I should put 24 1. And this 24 1 will say that these 24 bits in this IP address belong to the network part. And at the end, I will need 80. And this 80 here will say that this 8 bit in the host part, in the IP address, belong to the host part. No? When you configure a device, you need to specify some IP address of the device, the network of the device you need to specify. So at least you need to specify 2 information. One information will be the IP address of the device per se, and then the net mask. Remember that the net mask is a series of 1 in binary followed by a series of 0. You will always need these 2 information. Optionally, you will need a default gateway. So if you have more than one network, you will have routers. And in each computer that will belong to the internetwork, you will have to configure a default gateway. The default gateway is a way to specify to the computer what to do if you want to reach a remote network, a network where it is not part of. So normally when I want to reach a remote network, I have to send the packet to the router, and the router will take care of forwarding the packet to the remote network. So this is the objective of the default gateway. There is also some field here in Windows that are optional, which are the DNS server. DNS stands for domain name system, and it's a service. It's a client-server service where the client can query the server for example, to resolve a domain name to an IP address. So people have difficulty to memorize IP addresses, but the computer works with IP addresses. So people don't have problem to memorize www.jsu.edu. And if I ask you, for example, what do you think that will be the web server of IBM, I'm sure all of you will say, I'm sure it's www.ibm.com. Okay, because it's a company, it will be a .com. So we don't have problem to memorize that. But we do have problem, for example, to memorize 192.168.10.10. So when we serve the internet, we use domain name. But the computer only works with numbers, binary numbers. So we need a way to convert those domain name into an IP address. The DNS server is the one that will take care of that. For example, it will convert www.jsu.edu to one IP address or a list of IP address. It can be a list of IP address if we have, for example, load balancing. So you can imagine that big server like Amazon, like Google, that receive millions of requests in a second, do have load balancing. Otherwise, they will be very slow. They are fast because it's not at the end one computer that is behind, but it's a farm of computers, a lot of computers. So every time that you make a request in Google, the request comes and it is sent to one of the computers in the farm of computers. And this computer will take care of your request. We check the answer and we send you the answer. No? So it's why it can be one IP address or it can be a list of IP addresses when you resolve a domain name into an IP address through the DNS service, the domain name system or the domain name service. Okay, so let's see that. We talk about net mask and we say that it was a series of 1 followed by a series of 0. For example, here we have an IP address in binary. This IP address is 192.168.10.10. And I want to say that I'm going to break this IP address in two parts. The network part, which are the 24 bits that are here, and the host part, which are the 8 bits that are here. So to specify where I break the IP address into, I use the net mask. And the net mask say, for example, this one, say that this bit belongs to the network part. This one say that this bit belongs to the network part. This third one say that this bit, which is a 0, belongs to the network part. So at the end, here I have 24.1, which means that the first 24 bits of the IP address belong to the network portion. Now I have a series of 0. Every time that I have a 0 in the network mask, it means that the bit associated in the IP address belong to the host part. So this 0 means that this bit belong to the host part. This 0, this bit belong to the host part. Okay, until, for example, this 0 say that this bit, which is a 1, belong to the host part. And this 0 mean that this bit belong to the host part. So remember, a network mask will be a series of 1 followed by a series of 0. We cannot have a series of 1, then a series of 0, and again a series of 1. No, because we break it in two parts. So all the 1 say that those bits associated belong to the network part. And all the 0 say that those bits belong to the host part. Remember, all the network devices that will belong to the same network will have a same network portion, because this ID identifies the network. So if we belong to the same network, we have the same network portion. Now, of course, within the same network, we will have a different host portion because each device needs an IP address. And you cannot have duplicate IP address because an IP address have to identify a device on only one device. Okay, so you will not have in a network duplicate IP address. There must be, each device must have its own IP address. So it's why the host portion in the same network will be different for all the devices. Okay, so in 230, you have seen some operator that we use on binary, for example, the AND. So just as a reminder, 0 and 0 is 0. 0 and 1 is 0. 1 and 0 is 0. And 1 and 1 is 1. So the AND is 1 if and only if both operands are 1. No? In other case, if at least one of the operand is 0, the result of the AND will be a 0. So when we have a network, we have an IP address that is called the network address. And all the devices that belong to the same network will have the same network address. So the network address is also an IP address. How do we get the network address? We will do the bitwise AND between the IP address of the device and the net mask. So let's say, for example, a computer has this IP address, 192.168.10.10. And the net mask associated with the network is 255.255.255.0. And I would like to have the network address. So the way that you get the network address is that you do the bitwise AND between the IP address and the net mask. So I put the IP address here in binary. I put the net mask in binary. So 255 is 81. 255, 81, 255, 81, 0 is 80 in binary. And I'm going to do the bitwise AND. So whatever I have here, bitwise AND 0 will be what? What will be the result? If you do X, bitwise AND 0, it will be 0. So at the end, I don't need to do 0 and 0 is 0. 1 and 0 is 0. I don't need to do 1 by 1. I can just say every time that we have a 0 here, the result will be 0 because it will not depend on the value of the bit that we have in the IP address. Now, when we have a 1 in the net mask, what will happen? If I do X and 1, what will be the result? So X and 0 is always 0. And X and 1 will be what? X. Will be X, correct. Which means that here, you can lose your time if you want saying 0 and 1 is 0. 1 and 1 is 1. 0 and 1 is 0. Then 1 and 1 is 1. You can use your time. Or you can just say, every time that in the next mask I have a 1, I have just to copy those bits without changing them. Because X on 1 is X, which means that every time that I do a bitwise AND with 1, I maintain the value that I have here. So I just copy the 0 here, just copy the 1, just copy the 0. Okay, I can just copy them. So this will be the network address in dotted binary notation. So for people, we don't use the dotted binary notation. We use the dotted decimal notation. So I take this number and I convert it in decimal. So the first byte will be 192. The second byte will be 168. The third byte will be 10. And the last byte will be 0. So this IP address with this subnet, this IP address belongs to this network. It belongs to the 192.168.10.0 network. Okay? And when I have an IP address and I want to know to which network it belongs to, I will do the bitwise AND between the IP address and the net mask. And it will give me the network address. Okay, so we will do a lot of exercise on that to get the network address. Okay, let's talk a little more about net mask. So look, remember that a net mask is a series of 1 followed by a series of 0. So this is a valid net mask. If I put it in dotted decimal notation, it will be 255. Remember that 81 is 255. Dot 0, dot 0, dot 0. So that we will call that the dotted decimal notation. Now there is another notation that is called the forward slash notation or the side R notation. We call it also the side R notation. And in this notation, we put a forward slash and we put an integer. And this integer is the number of 1 that we have in the net mask. So here we have 81. So it will be in side R notation. It will be forward slash 8. Okay, let's see another example. 16.1, 16.0. Remember, it's a series of 1 followed by a series of 0. So in decimal notation, this byte will be 255. This byte will be 255. This byte will be 0. This byte will be 0. So this net mask is 255.255.0.0. Inside our notation, how many 1 I have? 16. So another way to write this net mask is forward slash 16. Let's see a third example. Here we have 24.1 followed by 80. We can just write it forward slash 24. In dotted decimal notation, it will be 255 for this byte, 255 for this byte, 255 for this byte, and 0 for this byte. Okay, now look at, this is an example that we have not seen up so far, no? We have 25.1, 8 plus 8 plus 8 plus 1, 25.1. So the forward slash notation will be forward slash 25. And of course I have 70. If I represent this net mask in the dotted decimal notation, it will be this byte will be 255. This byte will also be 255. This byte will also be 255, but the last byte will be 128. Okay, 128 is there in the sum. 64 is not there, 32 is not there, 16 is not there, blah, 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 is not there. So it's just 128. Look at this one. How many 1 we have in the net mask? 26, no? 8 plus 8 plus 8 plus 2. So it's 26. So with the forward slash notation or the side R notation, it will be forward slash 26. With the dotted decimal notation, it will be, this one is 255, dot 255, dot 255, dot 128 plus 64. 128 plus 64 is 192. So this is, the last byte is 192. Let's see this example. Here how many ones we have? 8 plus 8 plus 8, which is 24 for now, plus 3. 24 plus 3 is 27. So inside our notation, it will be /27. And in dotted decimal notation, this first byte will be 255, dot 255, dot 255, and this last one will be 128 is present, 64 is present, and 32 is present. So 128 plus 64 is 192. 192 plus 32 will be 224. So this is 224. Okay, and there are more examples here, but it's always the same thing. Remember, a net mask is a series of 1 and a series of 0. So if we have this net mask, how many bits I have in the IP address that are associated to the network portion? And how many are associated to the host portion? If we have the last net mask, the /30. What does it mean, the /30? That in the IP addresses?
30 network bits and 2 host bits.
Exactly, 30 network bits and 2 host bits. That's true. If I take this example, /27, it means that the first 27 bits belong to the network portion, and the last 5 bits belong to the host portion. Okay, remember, series of 1, all the 1, these say 12 bits belong to the network portion. All the 0 after 12 bits belong to the host portion. Okay, so let's take an example of a whole network. We are going to talk about this network, the 192.168.10.04/24. So this is the net mask. It means that the first 24 bits belong to the network portion, which means that the first 3 bytes belong to the network portion, and the last byte belong to the host portion. So which means that in this network, the IP address will start is 192.168.10.0 and go up to 192.168.10.255. Because just in the last byte, I will have flexibility to choose the bit. And if I have 8 bits that are free, I can go from .0 to .255. So how do we get the network address? In the host portion, we put all the bits in 0. Now we define some IP address that are called valid IP address. Valid IP address are IP address that you can assign to a network device. So the first IP address is not a valid IP address. It is called the network address. I cannot assign the first IP address to a network device. And the last IP address that we will get by putting all the host portion in 1 is also a special IP address. It is called the broadcast address. We cannot assign the broadcast address to the network device. On the broadcast address, we will get it by filling all the host bits with 1. Now, we will always in the network lose 2 IP addresses, the first IP address and the last IP address. The first IP address will be the network address, and the last IP address will be the broadcast address. In between these 2 IP addresses, all the IP addresses are valid IP addresses. So the first valid IP address, we will get it by filling the host portion with zeros, except the last bit that have to be in 1. And the last valid IP address, we will fill the host portion with 1, except the last bit that have to be in 0. Okay? So valid IP address are also called usable IP address. And they are also called host addresses or host IP addresses. So when I will talk about valid IP address, usable IP address, or host IP addresses, this is exactly the same thing. This is 3 terms and they are synonym. Okay? So I will use one of the 3 terms. It depends, no? I can use any of the 3 terms. Okay, the window calculator, we saw it last time. So this is the one of, I think, this is not Windows 10. It might be Windows 7. The one of Windows 10, oh yeah. The one of the Windows 10 is this one. This one is the one of Windows 7. So you know that if you go there, you can change the type of calculator. So you have a scientific calculator, and you have, for example, the programmer calculator. With the programmer calculator, you can specify the base. For example, if you click here, only the 0 and 1 key will be available because you are going to type a number in binary. If you click here, you are using the octal base. The octal base used from 0 to 7. If you click here, you are using the decimal base from 0 to 9. And if you click in hexadecimal, you are going to use the hexadecimal base from 0 to F. So 0 up to F, no? All this key will be available as you have seen last time, no? So you just open the calculator and you can walk. Remember that here we can specify if we want to walk with 1 byte, 2 byte, 4 bytes, or because it have byte, word, double word, and quadruple word. So it will be 1 byte, 2 byte, 4 byte, or 8 byte, no? So we saw that last time. Let me just show you the calculator again. So it is there. And let me put it over that. So you have the standard calculator, which is a basic calculator. The most interesting are the scientific calculator and the programmer calculator, no? And of course, if I am in decimal, I cannot press A, B, C, D, E, F. If I click here in hexadecimal, they are available. If I am in binary, only 0 and 1 is available. If I am in octal base, from 0 to 7 will be available, no? And let's say that you want to know how to convert 192 in binary, which is 11000000. You go here in decimal, you type 192, and you will have it here in binary, no? 11000000. And in hexadecimal, it will be C0. Remember that every group of 4 bits is 1 hexadecimal character, no? Okay, so normally when you set up a network, your server must have a static IP address, an IP address that does not change with time, always the same IP address. So clients know how to access the server because the IP address is always the same. For example, if you look at the IP address of Google, it's always the same IP address. So when you put in the browser www.google.com, it will be always resolved to the same IP address. So it's a server. In a server, you need a static IP address. Now, static IP address are, for example, for those machines, it's difficult to use static IP address because we need to put an IP address a different IP address in each machine. So I have to be sure that I don't repeat the same IP address. And here I don't know how many machines we have, but we might have 30 machines. So it's more complex to manage static IP address when I have a lot of end machine like that. Those are end machine. They don't offer service to the community. We don't have a web server running in this machine. This machine have web client, like a browser, okay? But they don't have a web server. They don't have a file server. They don't have a printer server. So they don't need a static IP address. So for that, there is a protocol that is called DHCP, Dynamic Host Configuration Protocol. So when you configure, this is a Windows machine, for example, you configure it to use DHCP, you will have to choose this option. Obtain my IP address and other parameter automatically, which means that when you boot your computer will try to communicate with a DHCP server and will ask the DHCP server, can you please give me my network configuration? And the DHCP server will tell the machine, use this IP address, use this net mask, use this default gateway. So all these machines, we don't know what is the IP address. And it's possible that today, one of these machines have one IP address. And when I come tomorrow, it have another IP address. Because every time that you start the machine communicates with the DHCP server and asks the DHCP server, can you give me my network configuration? And the DHCP server send it the parameter that it have to use. So if it's a DHCP server, like a process or a daemon, like we say in networking, that take care of assigning IP address to this computer, we will not have problem of duplicate IP address. If it's a person that go machine to machine and start putting IP address, I'm sure that the person will repeat IP addresses. Okay, because we do a lot of mistake. But of course, if you write a program like a DHCP server and you debug your DHCP server, it will not make mistake. Okay, every time that a new machine come up and need the network parameter, the DHCP server will give it a different IP address. It will not repeat the same IP address. Okay? So there are two ways to configure end device. It can be statically configured. It's good for small network, but not big network. It doesn't scale well. Or it can be dynamically configured with DHCP. Okay, let's see some vocabulary that we will be using. Unicast, broadcast, multicast. I'm sure you have heard about this before. So what is a unicast? A unicast is when we have only one destination. So for example, this computer wants to send a packet to the printer. This will be a unicast, only one destination. Broadcast will be all the devices in the subnet should receive a copy. So let's say that this computer wants to send a copy to all the other devices. So it sends it to the switch, and the switch take care to send it to the router, to this computer, to this laptop, and to this printer. This will be a broadcast. So it's one to all the other one. And there is something that we call a multicast. So to have multicast, we need computer that subscribe to a multicast group. They become subscriber. They say, I am interested, for example, in seeing the football game. So if this machine say, I'm interested in seeing the football game, and this machine say, I'm interested in seeing the football game, and this machine have the football game, it will send it, and these two machines need to receive all the packets that are associated with the football game. Okay, because they subscribe to the multicast group that is associated to the football game. So multicast is that, one to many. And the many will depend if they subscribe to the multicast group or they do not subscribe. For example, in this example, the router did not subscribe to the football game. This computer did not subscribe and this computer did not subscribe. So when the source, which may be a camera that is in the football field, send a packet, the switch have to take care to send the packet just to the subscriber of the football game. So we use special IP addresses to subscribe to a group. So those IP addresses that you see here, 224.10.10.5 in these two computers, is to show that they did subscribe to a common group, multicast group, which means that when there is a source that sends a packet to this multicast group, they both want a copy. Each one wants a copy of this packet. I have some slides that explain each case in a little more detail. So let's come back to a unicast. This computer wants to send something to the printer. So as you can see, each device in the network has its own IP address, and they are all different. So when this computer wants to send something to the packet to the printer, in an IP packet, you will have a source IP address and a destination IP address. So of course, this computer as source IP address is going to put its IP address. On this computer as destination IP address, since it wants to send it to the printer, is going to put this IP address, the IP address of the printer. So the packet will have two IP addresses, the source IP address and the destination IP address. So this packet, only the printer should receive a copy. This is called a unicast. Now, broadcast. Let's say that this computer wants to send a packet to all the other devices in the network. So, as source IP address, it will use its IP address. Now, as destination IP address, there is a special IP address, which is 255.255.255.255. This is called the limited broadcast address. When an IP packet has this IP address as the destination IP address, it means it's a broadcast, which means it's a copy for everybody, except the sender. The sender don't need a copy, but all the other devices in the network need a copy. So the packet will go from this device to the switch. The switch will send a copy to the router, send a copy to the desktop, send a copy to the laptop, and send a copy to the printer. This is a broadcast, okay? And we have a multicast. So as I was telling you, there is a range of IP address which is this range, from 224.0.0.0 up to 239.255.255.255. All the IP addresses between these two IP addresses are multicast IP addresses. So there is a lot. So let's say that at JSU, we offer multicast services. So we have, for example, a radio with classical music. So we can give one multicast IP address to this radio. And everybody that wants to listen the classical music have to subscribe to this group. But we have also, for example, people that like rock and roll. So we create also another group with another multicast IP address. And the people that want to listen the rock and roll have to subscribe. So I can subscribe at one point. When I subscribe, I need to receive the packet for this group, and I can unsubscribe, which means don't send me more this information. I'm not interested anymore. So here we can see that these two laptops did subscribe in a group, a multicast group, which is 224.10.10.5, as you can see. And this is a source for the multicast group. So it will send a packet. Source IP address, it will put its own IP address. And as destination IP address, it will put the IP address of the multicast group, which is 224.10.10.5. So this will arrive to the switch. And if the switch is modern, a little more intelligent than the old switch, it will just forward it to these two devices because they did subscribe. So modern switches are able, for example, when I subscribe to this multicast group, the laptop tells to the switch, hey, I am interested in this multicast group. So the switch already know, oh, there is a client for this multicast group on this link. So when I receive a packet for this multicast group, I have to send it to this client, to this subscriber. And the same thing will happen when this guy subscribes to the multicast group, it will let the switch know, hey, I entered this multicast group. So when you have a packet for this multicast group, send it to me. Okay? So they talk to each other, the devices, and they tell the other one what they need. So remember that multicast is one to many, and the many will vary. They have to subscribe to the multicast group. If nobody has subscribed, it will be 1 to 0. If just one device has subscribed, it will be 1 to 1. If 5 devices have subscribed, it will be 1 to 5. If 100 devices have subscribed, it will be 1 to 100. And of course, the list of subscribers can grow dynamically and can shrink dynamically also, no? Okay, so we have some IP address that we call the private IP addresses, and other that we call the public IP addresses. So the public IP addresses are the one that you assign to a device that should have access to the internet. And the private addresses are the one that you will put to a device that should only access the local information of the company. So we were forced to define private IP addresses due to the depletion of IPv4 addresses. So historically, TCP/IP was developed by the Department of Defense. It was a military project. And of course, that was in the 1970s when they did TCP/IP a long time ago, as you can see, 50 years ago. And when they define it, they decide that IP addresses should have only 32 bits. And of course, it was a huge amount of IP addresses, because at this time there were just few computers worldwide. So what happened is that the military at one point decided to release this technology, TCP/IP, and give it to the public, to the people. Like, for example, the GPS was also born in military context. And at one point, Bill Clinton signed to release the GPS to the public. So we have the GPS because Bill Clinton released it. And the drone technology also was born in the military. And at one point, I don't know which president allowed the drone to come to the public. So we have drone because one of the presidents said, okay, release it to the people. It doesn't have to stay a military technology anymore. And there is a lot of technology that they have, and they have not released. They will release it at one point. There is no doubt, no? So TCP/IP was a military project, and it was only, they think about it just to connect the computer of the Department of Defense, the military computer within the US. And of course, we have 2 to the power of 32 IP addresses because we have 32 bits in an IP address. It's a lot if you think about just the Department of Defense. But at the moment that they released TCP/IP, TCP/IP started to cover all the USA at the beginning and then started to spread out all over the world. And now TCP/IP is ubiquitous. It's everywhere. All your devices at home are intelligent, and they speak TCP/IP. So your fridge is intelligent. You control it with Alexa or Google Assistant or whatever solution that you choose, no? And you speak with your bubble, you speak with your switch, and you give them order. And all this through Wi-Fi, through network. So all these devices today need an IP address. So what happened? That we come to a point where we exhaust the IPv4 addresses. And the solution was, at the first point, was to create the private IP addresses. And then we came with a new version of TCP/IP, where we change IP in a new version. So the old version is called IPv4, and the new version is called IPv6, version 4 and version 6. We went from version 4 to version 6 because IPv5 is reserved in the US. They could not use IPv5. Okay, it's already a trademark. So they went from IPv4 to IPv6. Okay, so there are two blocks of IPv4 addresses that are private. So the first block is this block, 10.0.0.0/8. It includes all the IP address within this range. So all these IP addresses are private IP addresses. Then there is a second block, which is this block, 172.16.0.0/12. It includes all the IP addresses here, from 172.16.0.0 up to 172.31.255.255. All these IP addresses are private. And there is a third block, which is this one, 192.168.0.0/16, which include all the IP address in this range, 192.168.0.0 up to 192.168.255.255. Those are also private IP addresses. So there is an international organization that is called the Internet Engineering Task Force, IETF. So the Internet Engineering Task Force defined the standard of TCP/IP. It creates what we call the RFC. RFC stands for Request for Comment. So before you define a standard, you write the standard and you tell the community worldwide, tell me what you think about this standard. Tell me if we should change something. Tell me if we should approve it as a standard or if we should just drop it. So you open your proposal to the world community. An expert in networking and security look at your proposal and think about it, tell you, oh, I think it's good, but I would change this. So people worldwide, experts worldwide, discuss about your proposal. So you make the change. If you're lucky, you make the change that the expert require you to change. And at one point, the Internet Engineering Task Force, the IETF, approve your proposal as a standard. So this change over the IP of this block, of these three blocks of IP addresses, was approved as a standard, and this standard is called the RFC 1918. By the way, we can Google it now. Let me Google it so we can see it. So I'm just going to put here RFC 1918, and we will come to it. So look at IETF, which is Internet Engineering Task Force, and it's a text document where you will see the three blocks. So here are the blocks. The first block, the second and the third block. So that was, for example, accepted as a standard in February 1996. So the people that work on it is somebody from Cisco system, as you can see, somebody from Chrysler Corporation, somebody from RIP NCC, another person from RIP NCC, and another person from Silicon Graphics. Silicon Graphics was a company that was doing very good workstation, but it is dead now. Silicon Graphics, no? So it does not exist anymore, unfortunately. So this is a RFC. So a RFC have a number, the author, the date that it was approved as a standard, and what it is about. Okay, so here you can read it. It's very small. And when you write an RFC, you can only use text, which means that if you need to do a graphic, you need to use, for example, the less than, the greater than, the pipe, the plus. This is the only way to do graphics with an RFC. So let me show you, for example, the RFC of TCP. This is the RFC of TCP. They do need to do a state machine. So look at what they did. Let's go down and find it. So for example, look, with plus and minus, they need to make the stack of protocol. They did it like that because this is the only thing that is authorized. Let me show you, for example, look at that. This is a graphic. This is the way that a RFC allow you to do a graphic. But they have more ingenious graphic. Look at this one to show you the header of TCP. And we are going to arrive to the state machine. Oh, this is a state machine. So look at, for example, they need to do a row that go from this state to this state. Look at the arrow. You see? It is done with pipe, backslash, dash, and angle brackets. You see the arrow? Look at another arrow. There is a state here. They go from this state to this state in the state machine. They have to do it with ASCII, with text, because this is the only way that you can write an RFC. The RFC are only text documents. You cannot have a graphic document inside. If you want to do a graphic, you have to do like these people did in 1981, no? That's, of course, look at DARPA Internet Program. DARPA was a project of the DoD. So you can see, for example, Defense Advanced Research Project Agency. So that was the people that was doing TCP/IP at this time. And it was a military project, as I told you, no? So we have a lot of RFC to define TCP/IP, the suite of protocol that we will see in this course. Okay, so we have some IP addresses that are private. So some exercises will ask you, is this IP address a private IP address or a public IP address? So you need to know the ranges of which one is private and which one is public. No, those are the private one, the other one will be public. Okay, there is another group of IP address that is specific, that is called the loopback addresses. So those are the IP addresses that belong to this block, 127.0.0.0/8. So they go from 127.0.0.0 up to 127.255.255.255. All those are loopback addresses. People usually use this one, 127.0.0.1. And this is, those are IP addresses that reflect to myself. So when in a device, you talk about this, the IP address 127.0.0.1, it's myself. In another device, when you talk about the IP address 127.0.0.1, it's itself. So all these IP addresses are pointing to myself. So there is a bunch of IP addresses that are pointing to myself. There is another block, 169.255.0.0/16. So they go from 169.255.0.0 up to 169.255.255.255. Those are called the APIPA addresses or the link local addresses. So Microsoft uses them a lot. So when you have a DHCP server, when you have a DHCP client that try to reach a DHCP server on the network, do not have DHCP server, the Microsoft Windows operating system will choose a random IP address in this range and will assign it to the computer. So with this IP address, the computer can communicate locally, only locally, with other devices that also have an APIPA address. And there are 3 ranges of IP address to do exercises. So normally when we do exercises, we should use this IP address. And we should not use other IP address as I will do. Because the other IP address belong to a company or an institution in some part of the world. So you should not, in an exercise, put the IP address of an institution in some part of the world. So there are some block of IP address to do exercises. And those blocks are those 3 blocks that are here. So we should, but nobody do it. Even if they define 3 blocks for exercises, nobody use them. Everybody use random IP addresses that belong to some company. And well, we are used to do that and we get used to it. So that's fine. Okay. So the unicast addresses historically was divided in classes. And they define a total of 5 classes, A, B, C, D, and E. D is the multicast addresses, E is the experimental addresses, and A, B, C are block of unicast addresses. So the class A addresses are, we have several networks that are class A, and we have 128 network, we will see. And I have slides that give a little more information. But there are very few class A network, and they are huge. They have a lot of IP addresses inside. Class B addresses, the size is medium size. They still have a lot of IP addresses. But we have much more class B addresses. Class B network, I should say. Class C addresses are small. Every network that is class C is small. It has not a lot of IP addresses inside, but we have a lot of different class C networks. So this is historic, and that was defined in a request for comment with this number, 790. So you can go to this request for comment and read what they decided this time. So this is obsolete. We don't use it anymore, but it still be very common when you speak with somebody that work in the networking field. So we are going to see them, and we are going to see them with a lot of detail. So I'm going to start with the class A IP address. So remember that an IP address is an integer number of 32 bits. So 8888. No, the first byte, second byte, third byte, fourth byte. So if an IP address belongs to class A, the first bit will be a 0. So if the first bit is a 0, this IP address is a class A IP address. So there is another thing that is associated with a class A IP address, is that the separation between the network part and the host part is done here. If the separation is done here, what will be the net mask? How do I say that the first 8 bits belong to the network part?
28.0.0.
If I say 128.0.0.0, 128 is 1 and 7 0. So this one will say the first bit belong to the network. But here, the first 8 bits belong to the network because the separation between the network part and the host part is done here. So if I want to say the separation is done here, what will be the network address? The network mask. Sorry. How many one it have to have? 81. Because if it have 81, it say that the first 8 bits belong to the network part. And the last 24 bits belong to the host part. So if I want a separation here, I have to put in the net mask, I have to put 1, 1, 1, 1, 1, 1, 1, 1, saying that all these 8 bits belong to the network. Now to say that all these 24 bits belong to the host part, I will put 0, 0, 0 up to 0 here. So the net mask have to be 8, 1, followed by 24, 0. And this will be a /8 inside our notation. And in dotted decimal notation, this will be 255.0.0.0, isn't it? To say that there are 8 1 followed by 24 zeros, isn't it? So the separation is here. So if the separation is here, how many different network can I create in a class A? So look, this bit, I cannot change it. It have to be 0. And all those bits belong to the network part. So let's say that all those bits, you can change them as you want. You can put them in 0 or 1 as you want. So how many different network can I do? If I have 7 bits that are free to be 0 or 1, how many different value I can write? How many? 2 to the power of 7. And 2 to the power of 7 is 128. So we have 128 network of class A. You understand why? Because we have 7 bits that are free here. So with this bit, we have 2 possibilities. It can be 0 or it can be 1. With this bit, we have another 2 possibility. With this bit, we have another 2 possibility. And I say we have another 2 possibility 7 times. So 2 times 2 times 2 times 2 times 2 times 2 times 2, 7 times is 2 to the power of 7. So we can do 128 different networks of class A. Now, if I ask you, what will be the first byte of the first network? How do I get the first byte? Which means, what will be the minimum value for the first byte? If this byte, you want to minimize its value, and you are free to put 0 or 1 here, what value are going to put it to make it as minimum as possible? You will fill it with what? Of course, 70. If you fill it with 70, you will have the minimum value. And if you fill it here with 70, what will be the value of this byte? 0. So the first network start with 0 here in the first byte. And the last network. Now, if you want to maximize the first byte, How are you going to fill the 7 bytes, the 7 bits? Exactly, all with 1. If you fill all with 1, what will be the value 0, 1, 1, 1, 1, 1, 1, 1? It will be what? 127, correct. So the last network will be the 127 network. So the first network is the 0 network, and the last network is the 127 network. Okay? From 0 to 127, you have 128. This is 2 to the 7. I was saying that we have 128 network of class A. So the first one is the 0.0.0.0/8 network. And the last one is the 127.0.0.0/8. Now, let's see the host portion. If I ask you in each network, how many different IP address I will have? So you have here 24 bits. And you are free to fill them with 0 or with 1 as you want. How many different value can you do with 24 bits? Okay, because it is written there, but I need, huh?
255?
Yeah, but where is this number of 16,777,216 came from?
2 to the power.
2 to the power of 24. Of course, we have 24 bits here. Here we have 2 possibilities, 0, 1, time 2 possibility, time 2 possibility, blah, 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 time 2 possibility. So 2 times 2 times 2, 24 times will be 2 to the power of 24. So in each network, we have 16,777,216 different IP address. So as you can see, class A, we have very few networks. We have 128 networks, but they are very huge because each network have more than 16 million IP addresses. Okay, they are very, very huge. So remember, class A, the first bit have to be a 0. And the first byte will be between 0 and 127. So we say here the first byte will be between 0 and 127. And there is something that say, maybe we should say between 1 and 126, because this network is reserved, and this network is reserved. This one, we already talked about it. It's the loopback. We have a slide previously that say, this one is loopback. This network is loopback. So we cannot use it to put in network devices. And this one is also have a specific purpose. And we cannot use it to put in networking devices. Okay, let's see the class B. In the case of the class B, the first 2 bits have to be 1, 0. And the separation between the network part and the host part is done here. If the separation is done here, what will be the net mask? How many 1 I need and how many 0 I need? If I want to say the separation is here. How many 1 I need? So how many bits are on the left side? 16. So I need 16 1 in the net mask and 16 0. The 16 1 say that all those bits are network bits. And the 16 0 say that all those bits are host bits. So the net mask will be /16 inside our notation. And in dotted decimal notation, it will be 255, which is 81 here, dot 255, which is another 81 here, dot 0 to say that this byte is host, dot 0 to say that this byte also belongs to the host part. So these 2 bytes belong to the host part, while these 2 bytes belong to the network part. Okay, so this is the net mask. The net mask tells me where is the separation between the network part and the host part. So if I ask you how many network of class B we can create, what will be your answer? Why 16?
Because the first two are for the subnet mask.
The first two are 1, 0. We cannot, the first two byte or the first 2 bit. Okay, the first 2 bytes are for the network part, but this one is not free. This one have to be 1. So here I don't have 2 possibility. It have to be 1. So I have just 1 possibility. So it's 1 time. Here it have to be 0. How many possibility? 1. So it's 1 times 1 times 2. Here I can put 0 or 1. I am free here. Here I can put 0 or 1. So it's 1 times 1 times 2 times 2 times 2 times 2 times 2 times 2 times 2. So at the end it's what? 2 to the 14, and 2 to the 14 is this number, 16,384. So we have 2 to the 14 network. Okay? Now, how many IP addresses we will have in each network? So if I take a specific network, how many IP addresses I will have in each network? So to know the number of IP addresses that I have in each network, I go to the host portion. The host portion has 16 bits. All of them are free. So 2 possibility here, time 2 possibility, time 2 possibility, up to time 2 possibility. So what will be the total number of IP addresses? 2 to the 16. And 2 to the 16 is this number. So each network have a total of 65,536 IP addresses. Remember that we lose in a network, we lose 2 IP addresses, the first one and the last one. Why we lose 2 IP addresses? How is the first one called? We saw that in a previous line. The network address. It's a specific address in a network. It has a specific purpose, so I cannot assign it to a network devices. And the last one is the broadcast address. It's also have a specific purpose. So I lose 2 IP address. It's why here they take this number minus 2 and they get this number. And those are valid IP addresses, or are usable IP addresses, or are host IP addresses. Okay, host addresses, no? So look, in a class B, the first 2 bits have to start with 0, 1. So now if I ask you, what will be the range of value of the first byte? So what will be the minimum value here? How do I get the minimum value here in the first byte? What should I do to get the minimum value? The 6 bits that are free, I fill them with 0, because the first 2 bits are not free. They are 1, 0. I cannot change them. But those bits, I fill them as I want. So if I want the minimum value, I have to fill them 0, 0, 0, 0, 0, 0. And if you put them in 0, what will be this byte, the minimum value of this byte? 128. So they start, if the first byte is between 128 and another value that we will see, it will be a class B. Now, what will be the maximum value that I can have for the first byte? How do I get the maximum value? So remember, those I cannot change them, but all those are free. If you want the maximum value, what you will do with the 6 bits? You will fill them with 1, of course. So if you have 1, 0, 1, 1, 1, 1, 1, 1, and you convert it to decimal, it's going to give you 191. So if the first byte is between 128 and 191, I know that the IP address is a class B IP address. Okay? Let's see class C. So the class C IP address, the first 3 bits have to be 110. I cannot change them. They have to be 110. And the separation between the network part and the host part is done here. If the separation is done here, how many 1 I need in the net mask? 24, exactly, saying that all these 24 bits belong to the network portion, and all these 8 bits belong to the host portion. So the net mask associated will be a /24, which is 255.255.255.0. Now, if I ask you, how many class C network can we create? What will be your answer? Correct. Why to the power 21? Because all these 21 bits are free for me when I do network. Okay? So it's 2 times 2 times 2 times 2 times 2 up to time 2. So it's 2 to the 21, and 2 to the 21 is this number. So we have 2,097,152 network of class C, a lot of class C network. Now, if I ask you, how many IP addresses have each class C network? How many IP addresses have each class C network? Remember, the separation is here. This will be what? How many IP addresses of each network? 2 to the 8, of course, because look, here we have the host portion. Here I'm free to put 0, 1, so 2 possibility. Here I'm free to put 0, 1, another 2 possibility. Here I'm free to put 0, 1, so 2 possibility times 2 possibility times 2 possibility times 2 possibility, blah, 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 times 2 possibility is 2 to the power of 8. So we can have 256 IP addresses in total. We lose 2 IP addresses, the first one and the last one. The first one is the network address. The last one is a broadcast address. So valid IP address, we have 254. Okay? Now, if I ask you, what will be the minimum value for the first byte? How do you get the minimum value here? I fill this 5 bits with 0. Those are imposed. It have to be 1, 1, 0. I cannot change them. But I have 5 bits here that I can put either 0, 1. If I want to do the minimum value, I have to fill them with 0. So if you have 1, 1, 0, 0, 0, 0, 0, 0, this number is 192. So the minimum value of the first byte will be 192. What will be the maximum value of the first byte? I will fill this 5-bit with 1. So if you take 1101, 1111 is 223. So if the first byte is between 192 and 223, we know that it's a class C address. Okay? Let's see class D. Class D is multicast. In the multicast, we don't speak about subnet mask. So look at the class D addresses start with 1110, and all the remaining bits is to create different multicast subgroup. So how many multicast subgroup can I create? If I telling you all these bits is to create different multicast subgroup. So how many multicast subgroup can I create? Two to the 28, of course, because we have 28 bits that are free. So here we have two possibility, time two possibility, time two possibility, time two possibility, blah, 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 up time two possibility. So it's 2 to the 28. And 2 to the 28 is this number. Okay? So if I ask you, what will be the range of the first byte if the IP address is a multicast address? So we need to find the minimum value and the maximum value of the first byte. How do I get the minimum value? I will fill these 4 bits that are free for me to fill with 0. If you put here 0, 0, 0, 0, this number will be 224, which is 128 plus 64 plus 32. It will be 224. What will be the maximum value? I have to fill these 4 bits that are free for me to fill with 1. So 128 plus 64 plus 32 plus 8 plus 4 plus 2 plus 1 will be 239. Okay? So if the first byte is between 224 and 239, it will be a multicast address. And finally, we have the class E addresses, the experimental addresses. Those are for research. So people that do research in networking can use them as they want. So look, the first 4 bits have to be 1111. On all of them, you do whatever you want with them. So how many experimental IP addresses we have? So here, how many bits we have? 28. So 2 to the 28. This number is 2 to the 28. How can I identify if an IP address is an experimental IP address? I can look at the first byte. What will be the minimum value? You put here 0, 0, 0, 0. If you compute that in decimal, it will be 128 plus 64 plus 32 plus 16. And this is 240. Now, what will be the maximum value that I can have here in the first byte? I fill this 4 bit with 1111. If you fill this 4 bit with 1111, it will give you what? 255. So, class A, the first byte have to be between what and what? Between 0 and 127. Class B, the first byte have to be between what and what? Between 128 and 191. Class C, the first byte have to be between 192 and 223. Class D, the first byte have to be between what and what? 224 and 239. On class E experimental, the first byte has to be between 240 and 255. So just by saying the first byte of an IP address, you can say it's class, because they have range, and the range are not overlapping. They are different. So look, half of the IP address in the world are class A. A quarter of them are class B. 1/8 are class C. And here we have class D and class E. 1/16 are class D, and 1/16 are class E. Okay? So who manage the IP addresses? The world is divided in 5 NIC. NIC stands for Network Information Center. And they are the entity that manage the IP addresses. So America have 2 NIC. ARIN, which stands for American Registry Internet Number. And ARIM control North America and some island in the Caribbean. And we have another NIC, Network Information Center, which was LACNIC, Latin America and Caribbean Network Information Center. So they control South America, Central America, and some island of the Caribbean. Now, in Africa, we have AFRINIC, African Network Information Center. So they have all the networking resources on the African continent. In Asia and the Pacific, we have Asia Pacific Network Information Center, which control all the Pacific islands like New Zealand, Australia, Nueva Caledonia, Papua New Guinea, all these islands that are here, and all the part of the Asian continent like Japan, the 2 Korea, Vietnam, all these countries belong to Asia Pacific NIC. And this one, Réseau IP Européen Network Commander Center, control Europe, the Middle East, and some country in Central Asia. So Europe, like Spain, Portugal, France, Italy, Norway, all Europe. The Middle East. So the Middle East is this part of the world, no? Like Saudi Arabia, like Yemen, like Kuwait. This is the Middle East, and some country in Central Asia. Like, for example, Ukraine and other countries that are here in Central Asia. Okay, so they control all the resources. Okay, we are done with this part. I'm very sorry, nobody say anything. Okay, when I go over the time, let me know. Okay, I went 30 minutes over. I didn't realize that. I'm very sorry for that. Next time, just let me know. We are over the time and I will stop. Okay, thank you so much. I see you in 2 days.